In this lecture, we will learn about how Raman spectroscopy can be used to characterize graphene samples. Raman spectroscopy is perhaps the most powerful technique available for the characterization of graphene and other two-dimensional materials, and therefore we will dedicate this entire lecture to the study of this technique. Raman spectroscopy provides information about the atomic and molecular vibrations that can be used for sample identification and characterization. The technique involves shining a monochromatic light source such as a laser on a sample and detecting the scattered light. The majority of scattered light photons are of the same frequency as the excitation photon. This is known as Rayleigh or elastic scattering, which does not change the energy of the photon upon scattering. A very small amount of scattered photons, usually much less than 1% of the incident light intensity, is shifted in energy from the laser frequency due to interactions between the incident photons and the vibrational energy levels of the molecules in the sample. Molecular vibrational modes are also known as phonons, just like electromagnetic vibrations are known as photons. Plotting the intensity of this shifted light frequency, or the shift in the frequency, results in a Raman spectrum of the sample. The frequency shift is used as the x-axis in a Raman plot, and the band positions lie at frequencies that correspond to the energy levels of different molecular vibrations, and will therefore be characteristic of the available vibrational modes in the sample. Not all vibrational modes available in a sample are said to be Raman active. Some vibration modes do not result in a corresponding Raman scattering process. When a monochromatic laser light with frequency omega I excites molecules, it transforms them into oscillating dipoles. Such oscillating dipoles emit light of three different frequencies. First, a molecule absorbs a photon of frequency omega I. The excited molecule returns back to the same basic vibrational state and emits light with the same frequency omega I as seen here, as the excitation photon. This type of interaction is known as elastic or Rayleigh scattering. Secondly, a molecule which is in its ground vibrational state absorbs a photon with frequency omega I and then goes into an excited state. Part of the photon's energy is transferred into a Raman active vibrational mode with frequency omega 0, and the resulting frequency of the scattered light is reduced to omega I minus omega 0. This Raman frequency is known as the Stokes frequency. A molecule which is already in its excited vibrational state absorbs a photon with frequency omega I and goes into the excited state. In this third case, when the molecule relaxes, it returns to its ground vibrational state and in doing so releases a photon which carries with it the energy of the Raman active vibrational mode, and its frequency is shifted to omega I plus omega 0. This Raman frequency is known as the Anti-Stokes frequency. Normally, the number of molecules already in the excited state is many orders of magnitude smaller than the number of molecules in the ground state. Therefore, the probability of an incoming photon interacting with a molecule already in its excited state is orders of magnitude smaller than the probability of the photon interacting with the molecule in its ground state. So, the Stokes intensity is orders of magnitude greater than the anti-Stokes intensity, and anti-Stokes signal is not even detectable in most systems. When presenting the Raman spectrum of graphene or other systems, generally, only the Stokes peaks are presented, except in special circumstances where additional information can be gathered from the ratio of Stokes and anti-Stokes peak intensities. Another way of representing this process which you might encounter is by means of a Feynman diagram as shown here. In this diagram, wavy and straight arrows stand for photons and phonons respectively, while the dashed circles represent electron-hole pairs. Black dots and black squares represent electron-photon and electron-phonon interactions respectively. As a reminder, phonons refer to the molecular vibrational modes, just as photons refer to electromagnetic vibrations. Next, we look at the components of a Raman instrument, which might be used to obtain the Raman spectrum of graphene. The typical Raman system consists of these major components. First is the excitation laser source. This goes through the sample illumination optics to the sample stage. The light is collected through light collection optics, to which wavelength filters and selector optics are applied. Finally, the light reaches a photodiode array CCD or photomultiplier tube, which functions as the detector. And finally, the data goes to a computer for signal processing. A sample is normally illuminated with a laser beam in the ultraviolet, visible, or near-infrared range. Since frequency shifts arising from the Raman scattering are very small, the Raman scattered light has to be separated from the Rayleigh scattered light. This is usually done by means of a commercially available interference or notch filter, which cuts off spectral range of plus or minus 80 to 120 centimeter inverse from the laser line. This method is efficient in stray light elimination, but it does not allow the detection of low frequency Raman modes below 100 centimeter inverse shift. Modern Raman spectrometers use multi-channel detectors like photodiode arrays, or more commonly a charge-coupled device or CCD, to detect the Raman scattered light. Older Raman spectrometers are likely to use photomultiplier tubes. As mentioned before, the shifts observed in a Raman spectrum are directly related to the vibrational modes of the molecules, or in the case of graphene, the collective vibrational modes of the atoms in the graphene sheet. A phonon dispersion is a plot of the phonon momentum or wave vector versus the phonon frequency, and part of the phonon dispersion of graphene is shown here, limited to the higher energy or the so-called optical phonons, which participate in the Raman scattering process. In order for an electron and phonon to interact, there has to be a match of wave vector number between the two, or, in other words, the momentum of the scattering process has to be conserved. Usually, Raman scattering is able to probe only phonons close to the gamma point. However, in the case of the D peak, which we will encounter later, which is a defect-mediated mode, Raman spectroscopy can sample phonons close to the K point, despite the large momentum mismatch. This can also happen in the case of the 2D peak. However, because this is a double resonance process, no physical defect is involved, but rather a virtual state which plays the same role as a defect provides the momentum mismatch. Physically, these phonon modes or lattice vibration modes can be visualized as collective oscillations of the atoms in the graphene lattice. The G mode, as seen from the phonon dispersion, arises from either of two phonons of the same energy. These are known as degenerate phonons. The phonon of the transverse optical branch is the result of atoms vibrating in plane and in line with each other, as seen here, while the phonon of the transverse optical branch is the result of atoms vibrating in plane but orthogonal to the TO vibrations. The D mode and 2D mode both share the same phonon, which is a result of the atoms that form a hexagon vibrating towards and away from the center of the hexagon, as seen here. This is the so-called breathing mode because it results in alternating contraction and expansion of the hexagons in a graphene lattice. Indeed, in reality, the atoms do not choose to vibrate in just one of these modes, but rather in any direction in plane vibrations of the atoms can be resolved into one or more of the basic vibration modes seen here and can be expressed as a linear combination of these basic vibration modes.